In the last lecture, we were discussing the solution of the diffusion equation. The equation for the concentration field or the temperature field is usually written in this form, where the left side contains the time derivative and the change in concentration due to convection. Okay. So, this form, so normally this should be this term should usually be written as the divergence of V times C, okay, which is V dot grad C plus C times the divergence of V. Okay. You can expand this out in terms of Ex, Ey, Ez and partial by partial x, partial by partial y and partial by partial z, and satisfy yourself that this is true. And normally for incompressible flows, the divergence of the velocity is equal to 0, and for that reason it is written in this form as well, provided the flow is incompressible. So, we had scaled the velocity by characteristic velocity, the position by a characteristic length, and the divergence or the gradient operator is L times, okay, the scaled gradient operator is L times the dimensionless gradient operator, and the characteristic time scale we had scaled it by the convective time scale, that is L by Vc, okay, the length by the characteristic velocity. In terms of this, we get a dimensionless equation here, okay, provided C is suitably non-dimensionalized, which has this Peclet number, characteristic velocity times characteristic length divided by diffusion coefficient, okay, on the left side. And for flows that are of sufficiently small characteristic velocity or sufficiently small characteristic length, the Peclet number is small, and therefore, you can neglect the left side of this equation compared to the right side. And the diffusion equation is basically the Laplacian of the concentration field is equal to 0, or the Laplacian of the temperature field is equal to 0. This has to be solved in general in 3 dimensions. We had looked at some solution in the last lecture in a Cartesian coordinate system for a block, 2-dimensional block of length L, height h, in which the temperature is at different on different surfaces is different. The left and right surfaces are at T naught, the bottom at T A and the top at T B. And therefore, the Laplace equation for the temperature field when suitably scaled, okay, so we got this as the Laplace equation in terms of the dimensionless temperature. And when solving by separation of variables, if you recall, when we solved the unsteady separation of variables in one dimension, for the transient part of the temperature or the concentration field, the spatial boundary conditions have to be homogeneous. There is an inhomogeneous initial condition at initial time. Now, what we are solving for here is the steady state, okay, in 2 dimensions, okay, using separation of variables, and it is essential that the temperature field in any one of those dimensions be reduced to homogeneous boundary conditions. In this case, it is obvious that T is equal to T naught at both the left and the right boundaries, that is at the boundaries at x is equal to 0 and x is equal to L. Therefore, that can be identified as the homogeneous directions. Okay. So, that is the boundary condition is homogeneous at x is equal to 0 and at x is equal to L, provided I define the temperature as the difference between the local temperature and T naught. Okay. So, if I define that as the difference between the local temperature and T naught, then T star is equal to 0 at x is equal to 0 and x is equal to L. The inhomogeneous boundary conditions are in the y direction. Okay. T star is equal to T A minus T naught at y is equal to 0 and T B minus T naught at y is equal to h. So, we solve this equation and the solutions. Okay. So, in this particular case I have 2 terms. Okay. I have two terms, okay. One of them in the x direction, the other in the y direction. In the x direction is where I have the homogeneous boundary conditions. So, therefore, I have to write 1 by x d square x by dx square is equal to minus beta square. So, that the solutions are of the sine and cosine form, and only if they are of the sine and cosine form can they satisfy boundary conditions on two boundaries. If they were exponential, if they were not oscillating functions, if they were exponential, you could not satisfy the boundary conditions on both boundaries. Therefore, I have to assume minus beta square in the x direction, y direction is plus beta square, and I get the solution for beta as I pi by L. Should be noted that I pi by L is only if you have sine and cosine functions, okay, or in general if you have okay, the boundary conditions for the velocity being 0 at both boundaries. Then I will get a solution of the form sine of I pi x by L. If the slope was 0, if the derivative was 0 at both boundaries, then it has to be a cos function. And if the value is 0 at one boundary, the slope is 0 at the other boundary, then you get other types of solutions such as sine of I plus half 2i plus 1 by 2 pi, okay, x by L. Okay. So, the sinusoidal function in the x direction, and you have exponential functions in the y direction. Okay. Note that the eigenvalues in this case are also I pi y by L, okay, not I pi y by h, because this beta has to be the same for both the x and y directions. So, this solution that I have got here, it satisfies the equation because we use separation of variables, and it satisfies the boundary conditions at x is equal to 0 and x is equal to L. The coefficients, integration constants di and ci have to be calculated from the y boundary conditions. Okay. That is Ta minus T naught is equal to Ci plus di into, okay, e power I pi 0 by L. Okay. So, if you write down the y boundary conditions here, okay. So, the boundary conditions are of this form. Okay. This is for Ta minus T naught, this is for Tb minus T naught. So, these are an infinite number of coefficients Ci and di, okay, at both boundaries. Okay. So, these coefficients have to be evaluated at both boundaries. Relations. Okay. I multiply this by sine of j pi x by L on both the left and right sides, and integral from dx from 0 to L. Similarly, in this case, integral 0 to L dx sine j pi x by L, integral 0 to L dx sine of j pi x by L. Okay. On the right side, integral of sine I pi x by L times sine j pi x by L is just equal to is proportional to delta ij. Okay. So, I just get Cj plus dj on the left side. I can evaluate the right side by integrating, and therefore, I can evaluate both the constants Ci and di. Okay. In some cases, the inhomogeneous term may not be in the boundary conditions itself, it may be in the equation itself. Okay. An example of this is the flow in a rectangular channel. Okay. An example of this is the flow in a rectangular channel. Okay. So, a rectangular channel rectangular channel with coordinates x and y and z, sorry, let me use y and z, and x is the coordinate along the channel in the streamwise direction. X is the coordinate along the channel in the streamwise direction. Height is h, and width is w. So, the height in the z direction is h, width is w, and the flow is in the x direction V x. The flow is in the x direction V x. The equation for the flow, first of all, del dot V is equal to 0, which implies that partial V x by partial x plus partial V y by partial y plus partial V z by partial z is equal to 0 is identically satisfied in this case, because the flow is only in the x direction. So, these two derivatives are 0, because the velocity is 0 in that direction. Further, if the flow is fully developed, then the velocity is independent of x. That is obvious from this equation, dVx by dx has to be equal to 0. So, therefore, the mass conservation equation is identically satisfied for a fully developed flow, where the velocity is independent of the x direction. Streamwise momentum conservation equation. Recall, in vector form it is written as partial v by partial t plus v dot grad v is equal to minus grad p plus mu del square v. If we take the velocity in the x direction for a steady flow, the time derivative is 0. V dot grad v is V x partial V x by partial x plus V y partial V x by partial y plus V z partial V x by partial z. V z and V y are both 0, its flow is unidirectional, and from mass conservation partial V x by partial x is equal to 0. So, the left side of the equation just reduces to 0 in the x direction. So, 0 is equal to minus partial p by partial x plus mu partial square V x by partial y square plus partial square V x by partial z square. So, that is the equation for the unidirectional flow. So, that is the equation for the unidirectional flow. Boundary conditions. This is a second order differential equation in the y and the z directions. So, this is a second order differential equation in the y and the z directions. Therefore, you need two boundary conditions in each direction. The boundary conditions are that at the walls the velocity is equal to 0. That is, it is called the no slip condition. V x is equal to 0 at y is equal to 0 and w, and velocity is equal to 0 at z is equal to 0 h. So, those are the boundary conditions. Velocity is 0 at y is equal to 0 and w, velocity is 0 at z is equal to 0 and h. So, these are both homogeneous boundary conditions. These are both homogeneous boundary conditions. The inhomogeneous term, that is the what is driving the flow in this case, is actually this pressure gradient. And if I wrote equations for the y and z momentum equation, that is the equations for V y and V z. Since the velocities are 0, V y is equal to 0 and V z is equal to 0, the velocities are 0, the viscous terms and the inertial terms will all be 0, and basically I will get 0 is equal to minus partial p by partial y, and 0 is equal to minus partial p by partial z. So, therefore, the pressure is independent of the y and z coordinates. In other words, the pressure is a constant in the cross section. Okay. The pressure is a constant in the cross section. Therefore, the pressure depends only upon x, and dp by dx is a constant. Okay. dp by dx is a constant. You can easily verify that by taking the derivative of this with respect to x. We will get d square p by dx square is equal to 0, because Vx is independent of x. Okay. If you take the derivative of this with respect to x. Okay. So, therefore, dp by dx is a constant. Okay. So, that okay. Now, these two functions, these two homogeneous boundary conditions stipulate that the velocity is equal to 0 at both boundaries in the y direction and at both boundaries in the z direction. Okay. Therefore, the velocities can be expanded in a set of basis functions. Okay. Therefore, the velocities can be expanded in a set of basis functions as follows. Okay. Vx is equal to sigma I is equal to 1 to infinity, sigma j is equal to 1 to infinity of a I j sin I pi y by w sin j pi z by L. Okay. These sine functions are a complete and orthogonal set of functions which satisfy the boundary conditions in the case of the y coordinate, that the velocity is 0 at y is equal to 0 and y is equal to w, and satisfies the boundary conditions in the z coordinate, that the velocity is 0 at both z is equal to 0 and at z is equal to h. You can see that sin I pi y by w is 0 at 0 and at y is equal to w, it is just sin I pi, and sin j pi z by h is 0 at both z is equal to 0 and at h. Okay. So, basically in each direction what you are doing is, okay, so I have this, okay, so let's just take the y direction velocity Vx. Okay. What we are doing is that this is, let us say this is equal to w in the y direction, the velocity has to be 0 on both boundaries. Okay. Therefore, I am expanding the velocity in a series of functions, sine functions. The first one like this, the next one like this, the third one like this, and so on, okay, having more and more maxima and minima as I keeps increasing. Okay. Any function can be expanded in a series of functions like this. Okay. Similarly, in the j direction. Okay. Therefore, I can use this expansion in order to express the velocity field, and this expansion is substituted into the conservation equation. Okay. This expansion is substituted in the conservation equation. Okay. Note that the conservation equation contains the derivative of the velocities with respect to y and with respect to z, the second derivatives. Okay. Therefore, I will get partial square Vx by partial y square is equal to sigma I is equal to 1 to infinity, sigma j is equal to 1 to infinity aij. Okay. When I take the derivative, I get a minus I square pi square by w square. Okay. Sin I pi y by w sin h. If you take the derivative of sin alpha y 2 times, you will get alpha square minus alpha square times sin alpha y. Similarly, d square Vx by dz square is equal to summation I is equal to 1 into minus j square pi square by h square So, those are the two derivatives of the velocities which I now substitute into the conservation equation. Conservation equation minus partial p by partial x plus summation I is equal to 1 to infinity into minus of I pi by w the whole square minus j pi by h the whole square sine and how do I determine the coefficients aij? It is by the orthogonality relations. Okay. Recall the orthogonality relations, integral dx, sorry, let me write in terms of y. Okay. I will write that as sine of I pi y w and sine of m pi y by w. Okay. This is equal to w by 2 delta I m, okay, 0 to w. Okay. This we had derived in the last class. You reduce it to the product of cost functions and then you integrate it. Okay. This entire equation, what I will do is I will integrate, I will take this entire equation multiplied by sine m pi y by w sine n pi z by h, okay, dy dz integral between 0 to w dy and sorry dy is already there and integral 0 to h. Integral over both the y and the z coordinates. So, I will get the second term on this in this I will get summation I is equal to 1 to infinity, summation j is equal to 1 to infinity aij, okay, w by 2 delta I m into h by 2 delta j n. Okay. This whole thing, if you recall, on the right side was equal to 0. I am sorry, I should include this term here. Okay, I should include this term here. So, let me just include that term, okay, into minus I pi by w the whole square minus j pi by h the whole square. This is equal to 0. And now to evaluate the integral of this term times sine m pi y by w and sine n pi z by h. Okay. So, let me do that also separately. Integral 0 to h w of dy into sine m pi y by w, okay, which is obtained by multiplying this term by this term here and 0 to w. Okay. So, this will be equal to cos of m pi y by w, okay, divided by m pi by w, okay, between 0 and w. Okay. At 0 the cost function is just 1. Okay. At w you get cos of m pi. Cos of m pi is minus 1 if m is odd and plus 1 if m is even. Okay. So, I can write this as minus of minus 1 power m, okay, into W by m pi. Okay. And I do the same thing in the z direction. Okay. And then what I will get here is minus dP by dx into 1 minus 1 power m by m pi into 1 minus 1 power n by n pi into h into W. Okay. That will be the first term, and the second term I should recall that we have a viscosity coefficient here. So, I should write the viscosity coefficient also here. Okay. So, once I do the summation, once I implement the delta functions, then I just get A and m. So, I can remove the summation, remove the delta functions, and just write this as A m n. Okay. And remove the delta functions and remove the summation. Okay. So, this gives me the solution for A m n is equal to minus 4. You can see that the W and the H's will cancel out on both sides, okay, into 1 minus 1 power m, okay, into 1 minus 1 power n, okay, by mu m n pi square into m square. I am sorry, I should have changed the, when I did the change from I to m, I should have done it over here as well. So, this should be m and this should be n. Okay, because I had when I had a summation over delta I m, I remove the summation and change all i's to m. Okay, when I have summation over delta I m, summation over I for delta I m, I remove the summation and change all the i's to m. Okay. So, this becomes m square pi square by W square plus n square pi square by h square whole inverse into dP by dx. Okay. Okay, that is the final solution. Okay. Recall this negative sign. That is because for the flow to be in the positive direction, dP by dx has to be negative. Pressure has to decrease with x, so that Vx is positive. Therefore, dP by dx is negative if Vx is positive. Okay. So, that is because the flow has to be down the pressure gradient. Okay. So, this gives us the solution for the velocity field. Okay. This gives us for the solution for the velocity field. Vx is equal to sum, okay, m is equal to 1 to infinity, sum n is equal to 1 to infinity, okay, of A m n, okay, into sine m pi x by L sine m pi y by L n pi z by h. It should not be L, it should be W. Where A and m is given, A m n is given by these set of coefficients. Okay, A m n is given by these set of coefficients. Okay, so this is the solution for A m n. So that is the separation of variable solution for the flow in a rectangular channel of width W and height h. Now we can find out what is the flow rate. Okay, so the flow rate, okay, I will call that as V dot is equal to integral 0 to W is dy integral 0 to h dz of summation A m n sine of m pi y by w sine of n pi z by h. Okay. And you can do the summation, okay, summation over m summation over n is equal to 1 to infinity, and you will get this as summation over m is equal to 1 to infinity, summation n is equal to 1 to infinity a m n into 1 minus minus 1 power m into 1 minus minus 1 power n w h divided by I j times pi square. Okay. So, that will be the solution. And the average velocity V average is just equal to V dot by W times H, okay, which will be the same thing, summation m is equal to 1 to infinity summation a m n into 1 minus okay, by m n pi square. I am sorry, this has to be m times n. Okay. So, that is the solution where I have substituted this a m n, okay, from here. Okay. And you can do a series expansion, you can include a finite number of terms and actually evaluate what this is. Okay. So, usually up to about 5 terms is sufficient to give you an accurate result for the average velocity up to 2 decimal places. Okay. So, you can use a truncation of this expression. Okay. So, this is an example of the I am sorry, there should be a dp by dx here. I should the velocity flow rate is related to okay, where a m n is related to minus of dp by dx as shown here. Okay. So, the velocity is linear in the pressure gradient with a coefficient which is given by this summation. Okay. The coefficient is given by this summation. So, I can include a finite set of terms in the series and solve this problem in order to get the velocity profile. So, these are 2 examples of separation of variables in a Cartesian coordinate system. Next class I will look at separation of variables in a spherical coordinate system for the diffusion problem. I will continue this in the next lecture. I will see you then.